Hi, my name is Samuel. Today I'll be presenting my project, and it's on Geno Climate Time Series forecasting, where the goal of this project is to use system identification tools, stationarity diagnostics, decomposition, and autocorrection analysis to design and justify a forecasting model for hourly air temperature. I will walk you through this in 4 parts. First, the dataset and the forecast variable. Second, the diagnostic stage, time series plot, stationarity test, STL decomposition, and ACF analysis. Third, the modeling plan I'm proposing anchored around seasonal ARIMA with exogenous repressors. Finally, the validation protocol and the risks I see going in. The final slides cover the timeline. The forecast variable is T, air temperature in degrees Celsius measured at the Bettenberg weather station in Jena, Germany. The proposal calls for at least 3 numerical drivers. These datasets give me 13 covering pressure, dew point, 3 forms of vapor, pressure, specific humidity, weather vapor concentration, air density, wind speed, gas speed, and wind direction. I will target 3 focus horizons: 1 hour for short-term operational use, 24 hours for daily planning, and 168 hours, that's a week, for long horizon stress testing. The data comes from Max Planck Institute of Biogeochemistry. It's a public, non-classified meteorological record covering January 2009 through December 2016, 8 full annual cycles. The raw cadence is 1 observation every 10 minutes. I resampled to hourly means to match the proposal exactly, giving 70,000 equally spaced records. Because everything comes from a single station, I avoid the cross-station alignment issues that dog multi-source studies, which means more of the modeling effort can go into the dynamics rather than data cleaning. Distribution and seasonal subseries. 2 views of the same series. On the left, the marginal distribution of hourly temperatures, roughly bell-curved mean around 9.4 degrees, with a slight bimodal tendency you can see in the shoulders. That's the alternation between winter and summer regimes. On the right, the box plot of temperature by month, January and February medians sit near 0. July and August near 19. Within each month, the interquartile range is 15 to 25 degrees. Large daily variations on top of the seasonal mean. The takeaway, the marginal density is a mixture across seasons, which is exactly the fingerprint of seasonal norm stationarity. Pearson cross-variable correlation. Pearson correlation metrics are 14 variables. 3 things stand out. First, the temperature variables, T, T-pot, T-dew, are very tightly correlated, often above 0.9. Second, the 3 vapor pressure variables from a clear cluster, saturation, actual, and deficit, are nearly redundant. Third, air density rho is strongly negatively correlated with temperature, exactly what the ideal gas law predicts. The practical consequence, if I would throw all 13 drivers into Sarimax, I will have severe multi-correlarity. So in the modeling stage, I restrict the exogenous set to a low correlarity subset. Pressure, correlative humidity, density, and wind speed. Time series plot. 8 years of hourly temperature. The annual oscillation is dominant feature. Summer peaks around 30 to 35 degrees. Winter troughs reaching minus 15 to minus 20. There is no obvious linear trend over the 8-year window, and we'll quantify that in a moment with the STL strength measure. Visually, the mean is clearly not constant, which is enough on its own to suggest non-stationarity. Rolling mean and variance. To make the non-stationarity rigorous, here are the two rolling mean and rolling variance computed over 720 hours. That's roughly 30 days window. The rolling mean on the top panel sweeps sinusoidally between minus 20 degrees in winter and plus 20 in summer. The rolling variance on the bottom is also cleanly non-constant. It spikes during seasonal transition. A genuinely stationary process would yield to flat horizontal lines for both. The fact that neither is flat tells us the series violates the stationarity definition. Stationarity tests ADF and KPSS, two formal tests captured straight from my Python script. What you see on the left is the actual terminal output. The augmented Dickey-Fowler statistics is minus 9.5, far below the 1% critical value of minus 3.43, with a p-value below 10 to minus 4. So ADF rejects the unit root null. The KPSS statistics is 3.9, far above the 1% critical value of 0.74. So KPSS rejects the stationarity null. At the first glance, this looks contradictory. They are not. Read together. They are saying the series is mean reverting in unit sense. There is no random walk because it's non-stationary because of deterministic seasonality. This is actually the diagnosis Heinemann documents for strongly seasonal time series, and it tells me the right pre-processing step is seasonal differencing, not ordinary differencing. STL decomposition. STL decomposes the daily average series into trend, seasonal, and remainder. The trend panel shows a very gentle drift between roughly 8 and 10.5 degrees over 8 years. The seasonal panel shows the dominant annual cycle. The residual are very comparatively small to make this quantitative. I use the Wang-Smith-Heinemann strength measures. The formula is in the report. The trend strength is 0.0584 and the seasonal strength is 0.8076. The conversion is that a strong above 0.64 counts as strong, so the trend is almost negligible, while seasonality is ambiguously dominant. This is constant with what we saw in the rolling mean slide and gives the clearest mandate yet. Any model that doesn't explicitly handle the annual cycle is going to lose. ACF. The autocorrelation function with 200 lags and 95% confidence bound. 3 observation. First, the lag 1 ACF is essentially 1.0, almost perfect persistence from 1 hour to the next. Second, every single bar over 200 lags stay well above the confidence band, White noise is decisively rejected. Third, the decay isn't monotone. It has an oscillating envelope with peaks at multiples of 24 hours and a slower envelope reflecting annual cycle. Slow ACF decay rules out a pure moving average model and demands an autoregressive component. PACF. The partial autocorrelation function tells us which AR logs actually carry independent information after controlling for the others. It cuts off sharply after the first one or two logs, and there is a clean spike at log 24, the daily period. That's the textbook signature of a seasonal ARIMA structure with seasonal periods of 24. Between ACF and PACF, the model class is essentially picked for me. Why autocorrelation modeling is justified. Stepping back from the diagnosis, here is why an autocorrelation-based approach is right tool for these datasets. Past values carry strong predictive information. The slow ACF decay proves it. The seasonal period is empirically identifiable from data, not assumed. The persistence is too long for a moving average model, so we need an AR component. Seasonal differencing at 24 lag will induce stationarity in difference series, and a long order ARIMA will then fit the residual. This is a classical Box-Jensen workflow, and it gives us a parsimonious, interpretable, fast model, which matters for this course. Proposed model, SARIMA X. Concretely, here is the modeling plan. Pre-processing seasonal difference at 24-hour period, then retest stationarity. Two baselines. Seasonal naive, predict the temperature from 24 hours ago, and persistent, predict the temperature from 1 hour ago. The core model is a SARIMA grid search over P, Q in 0, 1, 2, and PQ in 0, 1, with D equals 0 and D equals 1. I will select by AICC and confirm out of sample. Then the SARIMA adds the low correlarity exogenous subsets: pressure, relative humidity, density, airspeed, and airspeed. As benchmark, I will compare against three modern approaches: Prophet for fast automatic decomposition, an LSTM with a 168-hour input window, and an informal transformer for long horizon comparison. The point is to make the case for SARIMA or show clearly where it loses. Validation and metrics. Validation is rolling origin cross-validation, which is the time series equivalent of k-fold and avoids look-ahead leakage. I train on a window, evaluate on the next 24 hours, advance by a week, and repeat. The final 10,000 hours of the record, about 13 months, are held out for the final output report. Metrics: RMSE, MAE, MAPE for point forecast and 95th percentile prediction interval coverage, and width for probabilistic comparison. Since SARIMA gives me interval natively, the model selection happens on the cross-validation folds, not on the holdout. The holdout is reported once. Risks and timeline. I want to service upfront one multicorrelarity among the thermodynamic regressors addressed by the defensive subset, two SARIMAX fitting cost on 70,000 samples with seasonal period 24. Feasible but not free. So our budget: compute time, 3 kpss bandwidth, sensitivity. The statistic varies with the lag truncation choice, but the qualitative decision to reject stationarity is robust across reasonable bandwidth. For 8 years in is too short for a genuine climax trend claim. I will be careful not to overinterpret the small but non-zero FT. The timeline gives me 2 weeks for baseline and Sarima, 2 for Sarimax, 2 for neural benchmark, and a final week for the write-up. So this is the work that I've done so far, and this is the end of the presentation. Thank you.